Drop something into a black hole, and it is gone. Not gone the way a coin dropped into deep water is gone. Not recoverable in principle with better equipment. Not traceable if you had the right instruments. Gone in a way that has no analogue in ordinary experience. Gone in a way that the greatest physical theories ever constructed cannot fully agree on. Gone in a way that has kept the most brilliant minds in physics in genuine, unresolved disagreement for half a century. That disagreement is not about whether black holes are real. They are. We have photographed them. We have detected the gravitational waves produced when two of them collide. We have watched stars orbiting the supermassive black hole at the center of our own galaxy for decades and measured its mass to extraordinary precision. The existence of black holes is not in question. What is in question is what happens at the center. At the center sits a singularity. And that single word is where the most successful theory of gravity ever constructed meets the edge of its own ability to describe reality. At that point, the numbers that describe reality do not simply become large, they become infinite. And infinite is not a physical answer. It is a signal that the theory producing it has been pushed beyond the boundary of what it can describe. A calculator returning an error has not told you the answer is error. It has told you the question exceeded its range. The singularity is that error, returned by the most successful theory of gravity ever constructed, sitting at the center of every black hole in the universe, unresolved. And the reason it remains unresolved is not that physicists have not tried hard enough. It is that the two theories which should together produce the answer are speaking completely different languages. One theory describes the universe at its largest scales: galaxies, spacetime, gravity, the geometry of the cosmos. The other describes the universe at its smallest scales: particles, fields, quantum behavior, the discrete nature of energy. Each one works with breathtaking precision in its own domain. Aimed at the same point, they contradict each other in a way that neither framework can resolve alone. Think of it like two maps of the same city drawn by two different cartographers using two different systems of measurement. Each map is internally consistent. Each one correctly describes the streets and buildings in its own units. But where the two maps overlap, at the one location both cartographers tried to describe simultaneously, the measurements are irreconcilable, not approximately off, fundamentally incompatible, and that location is the singularity. What does it actually mean for space-time to become infinite at a single point? Why does the theory of gravity demand it? And why does the theory of the very small look at that demand and find it not just unlikely but physically forbidden? If you like exploring questions like these, feel free to leave a like and subscribe. And if there is something about the universe you find yourself wondering about now and then, drop it in the comments. It might become the next question we dig into. For now, let's get back to that question. The answer begins with what general relativity actually says gravity is. Not a force, not a pull, something more fundamental than either. Something that changes what space and time mean in the vicinity of mass, and something that followed to its logical conclusion inside a black hole leads inevitably to a point where space and time as we understand them cease to exist. General relativity is not a theory about gravity in the way a theory about wind describes air moving from one place to another. It is a theory about the geometry of space-time itself, about the shape of the four-dimensional fabric in which every event in the universe occurs, and its central claim is something that took the scientific community years to fully absorb. Mass curves space-time, not mass attracts. Other mass through a force that reaches across empty space. Mass changes the geometry of the space and time around it, and what we call gravity, the pull you feel toward the ground, the orbit of the Earth around the Sun, the bending of light around a massive object, is not a force at all. It is the natural consequence of objects moving through curved space-time along the straightest paths available to them. Picture a stretched rubber sheet. Place a heavy ball at the center, and the sheet curves downward around it. Roll a smaller ball across the sheet and it curves toward the heavy one. Not because a force is pulling it, because the geometry of the surface it is traveling across has been changed by the presence of the heavy ball. The smaller ball is following the straightest path available on a curved surface. General relativity says space-time works like that, except in 4 dimensions, and with a precision that has been confirmed by every test ever devised, from the bending of starlight around the Sun, measured during a solar eclipse in 1919, to the gravitational waves detected by LIGO a century later. Now take that framework and apply it to a collapsing star. A star massive enough that when its nuclear fuel runs out, the outward thermal pressure disappears and nothing remains to resist gravity. The core collapses, the material compresses, the density rises. The curvature of space-time around the collapsing core increases with the density. At a certain density, the curvature becomes so extreme that the escape velocity at the surface exceeds the speed of light. Nothing can move fast enough to escape. The boundary at which this occurs is the event horizon. Everything inside it is causally disconnected from the rest of the universe. No signal, no particle, no information of any kind can cross outward through it. Inside the event horizon, the equations of general relativity describe a geometry that does something deeply strange. The direction that was previously pointing toward the center of the star, the spatial direction inward, becomes the future. Not a direction you can choose to move in or avoid. The future. The way time points forward outside a black hole, always advancing, never reversing, the direction toward the singularity inside a black hole becomes mandatory in the same way. Everything inside the event horizon is moving toward the singularity the way everything outside moves toward tomorrow. Not because it is being pulled, because that is the geometry of space-time inside the horizon. You cannot avoid the singularity inside a black hole for the same reason you cannot avoid next Tuesday outside one. It is not in front of you. It is in your future. And general relativity's prediction of what that future contains is precise. As the infalling material continues toward the center, the curvature of space-time continues to increase. The density continues to rise. The tidal forces, the difference in gravitational pull between one side of an object and the other, grow without limit. At the center, the curvature becomes infinite. The density becomes infinite. The tidal forces become infinite. Space-time does not become extremely curved at that point. It ceases to be describable by the mathematics of general relativity at all. This is what general relativity predicts at the endpoint of gravitational collapse. Not a very dense object, not a compressed remnant, a point at which the geometric description of space-time that general relativity provides reaches values the theory itself cannot assign physical meaning to. The prediction is not that something strange happens at the center. The prediction is that the framework for describing what happens breaks down entirely. And that breakdown is not an accident of the mathematics or an artifact of idealized assumptions about perfectly spherical collapse. It is a theorem, a mathematical proof that under very general conditions the singularity is not just possible, but inevitable within general relativity. That proof came from Roger Penrose in 1965, and it changed how physicists understood the theory they were working with. Before Penrose, the singularity could be dismissed as an artifact, a consequence of assuming perfect symmetry in the collapsing star. A real star is not a perfect sphere. It rotates. It has irregularities. It is not composed of uniform density material distributed with mathematical precision. The early solutions to Einstein's equations that produce singularities were derived under idealized conditions. Perhaps the singularity was an idealization too. Perhaps in a realistic collapse the infalling material would miss the central point, swing past it, redistribute, and the singularity would be avoided. Penrose closed that escape route permanently. His 1965 theorem did not assume any particular geometry for the collapsing star. It did not require perfect spherical symmetry or uniform density or any other idealization. It required only three things. That general relativity correctly describes the geometry of spacetime. That matter satisfies a reasonable energy condition, meaning it does not have negative energy density in a way that would violate every known form of matter, and that a trapped surface exists somewhere inside the collapsing region. A trapped surface is a closed two-dimensional surface where even the light rays pointing outward are being pulled inward by the curvature of space-time. Once a trapped surface forms, Penrose showed, a singularity is mathematically inevitable regardless of the shape or composition of the collapsing object. The proof does not depend on what happens at the center. It depends only on the global geometry of spacetime once a trapped surface has appeared. The concept Penrose used to define the singularity is called Geodesic Incompleteness, and it is worth understanding precisely because it captures what a singularity actually is at the deepest level general relativity can describe. A geodesic is the path a freely falling object follows through spacetime. In flat spacetime, a geodesic is a straight line. In curved spacetime, it is the curved path produced by the geometry. The orbit of the Earth around the Sun is a geodesic. The path of a light ray bending around a massive object is a geodesic. Every object not subject to any force other than gravity follows a geodesic through spacetime. In a well-behaved spacetime, every geodesic can be extended indefinitely in both directions. Follow any freely falling path forward or backward, and it continues without interruption. The spacetime has no edges, no endpoints, no places where the path simply stops. A geodesic incomplete spacetime is one where some geodesics cannot be extended beyond a certain point, where a freely falling path reaches a boundary in finite time, and there is nothing beyond it. Not a region of extreme curvature that the path passes through and emerges from. An endpoint, a place where the path terminates, and the concept of what happens next has no answer within the framework of the theory. This is what the Singularity Theorems proved, that inside a black hole geodesics are incomplete, that a freely falling observer following a path toward the center will reach a point in finite proper time beyond which general relativity cannot say what happens. Not because we lack the computational power to follow the equations further, because the equations themselves break down. The curvature quantities that appear in Einstein's field equations diverge. They become infinite, and a theory built on finite, well-defined geometric quantities cannot operate in a regime where those quantities are infinite. The singularity is not a place inside the black hole. It is the termination of paths through space-time. It is the answer general relativity gives when asked what is at the center, which is not an answer at all, but an admission that the question has reached the boundary of what the theory can address. What makes this deeply uncomfortable is that the boundary is not at some exotic scale requiring new physics to reach. A stellar mass black hole has a singularity that an infalling observer reaches in a matter of seconds after crossing the event horizon. The proper time to the singularity is short. The curvature at which the theory breaks down is enormous, but it is a finite number that gets reached in finite time along a finite path. The breakdown is not infinitely far away in some asymptotic limit. It is close. It is reachable. And general relativity, the theory that predicted it, has nothing to say about what lies beyond it. Something else must. And the most natural candidate is the theory that governs the behavior of matter and energy at the smallest scales. The theory that has its own extraordinary precision and its own carefully tested framework, quantum mechanics, which looks at the singularity and does not just find it unlikely, it finds it structurally forbidden by one of its most fundamental principles. The Penrose theorem of 1965 was the first singularity theorem. Stephen Hawking extended it in the years that followed, producing a series of theorems that broadened the conditions under which singularities were mathematically inevitable. Together, the Penrose-Hawking singularity theorems constitute one of the most important results in the history of general relativity. Not because they describe exotic edge cases, because they showed that singularities are not accidents or artifacts. They are built into the structure of the theory under conditions that the observable universe actually satisfies. To appreciate what the theorems actually say, it helps to understand what they do not say. They do not say that the matter falling into a black hole gets compressed to infinite density in any physically meaningful sense. They say that the geometric description general relativity uses to track that matter reaches a breakdown point. The theory's own variables diverge, whether the matter itself does something physically infinite, or whether it does something the theory simply cannot describe, is a distinction the theorems cannot address. They operate within general relativity, and they identify where general relativity fails. What lies beyond that failure is outside their scope. They also do not say anything about what an observer falling toward the singularity would experience. General relativity can track that observer's path up to the point of geodesic incompleteness. It can calculate the tidal forces stretching and compressing the observer as the curvature increases. For a stellar mass black hole, those tidal forces become lethal long before the singularity is reached. For a supermassive black hole with a mass billions of times that of the Sun, the tidal forces at the event horizon are gentle enough that an infalling observer would notice nothing unusual at the moment of crossing. The singularity in that case would be reached later, in finite proper time after an extended period of apparently normal free fall through an interior that looks geometrically unremarkable until the curvature suddenly diverges. What the theorems do say is precise and consequential. Under the following conditions, a singularity is inevitable. General relativity holds. The energy conditions are satisfied. A trapped surface exists. Those three conditions are not exotic. The energy conditions are satisfied by every known form of matter and energy in the universe. Trapped surfaces form whenever sufficient mass is concentrated within a sufficiently small region, and general relativity has passed every observational test ever devised for it. The theorems therefore say that singularities form in the real universe, not in idealized mathematical models, in the actual universe, wherever black holes exist. And black holes exist throughout the observable universe in enormous numbers. Every galaxy appears to contain a supermassive black hole at its center. Stellar mass black holes form continuously as massive stars exhaust their fuel and collapse. The universe is populated with singularities on the general relativistic description, endpoints of geodesics, places where the geometric description of spacetime terminates. Stephen Hawking later applied similar reasoning to the Big Bang, running time backward and showing that the same conditions that produce singularities at the endpoints of gravitational collapse also produce a singularity at the origin of the universe. The Big Bang singularity is the geodesic incompleteness of paths traced backward in time rather than forward. The universe, on the classical general relativistic description, began at a point where the theory breaks down in exactly the same way it breaks down at the center of a black hole. Two types of singularity, one at the beginning of time, one at the endpoints of gravitational collapse distributed throughout space. Both inevitable consequences of the same mathematical structure, both representing the same failure of the same theory to describe what is actually happening at its own predicted limits. The theorems do not resolve the singularity, they confirm it. They take the prediction from a feature of idealized solutions and elevate it to a theorem about the theory itself. General relativity, applied consistently and honestly, predicts its own breakdown. It predicts places where it cannot tell you what is happening. And the intellectual honesty of that prediction is one of the reasons physicists take it seriously, rather than dismissing it as a sign that the theory is simply wrong. The theory is not wrong, it is incomplete, and the incompleteness is not random. It concentrates at a specific scale. A scale where the quantities general relativity treats as smooth and continuous becomes so extreme that a completely different framework must apply. A framework that insists at its foundations that smooth and continuous is never the full story. The word infinite gets used casually, infinitely patient, infinitely grateful, an infinite number of possibilities. In ordinary language, infinite means very large, larger than expected, beyond easy counting. It carries a sense of scale rather than a precise mathematical claim. In physics, infinite means something categorically different, and when a physical theory returns infinity as the value of a measurable quantity, it is not saying that quantity is very large. It is saying the theory has reached a boundary beyond which it cannot operate. To see why infinity is catastrophic rather than merely extreme, consider what a physical theory actually does. It takes a set of quantities describing a system at one moment and produces predictions for how those quantities will evolve. Density, pressure, curvature, temperature, numbers, finite numbers that can be measured, compared, and used as inputs to further calculations. The entire machinery of a physical theory depends on these quantities being finite and well-defined at every point in the calculation. When a quantity becomes infinite, the machinery stops. You cannot add infinity to a finite number and get a meaningful result. You cannot divide by infinity and recover useful information. You cannot use an infinite density as an input to calculate what happens next, because the output of that calculation is undefined. The theory does not produce a wrong answer at the singularity. It produces no answer at all. The computation simply fails. Think of it like a map. With a region marked here, there be nothing, not unknown territory, not uncharted, but real. A region the map explicitly declares outside its own descriptive capacity. The singularity is that region on the map of general relativity, not a place the theory describes badly, a place the theory cannot describe at all. But the problem runs deeper than computational failure. Infinite density is not just mathematically awkward, it is physically absurd in a specific way that points directly to what is missing. Density is mass per unit volume. Infinite density at a point means finite mass compressed into zero volume, a point with no spatial extent containing a finite amount of matter. Every property of that matter, its energy, its gravitational influence, its interaction with everything around it, concentrated into a geometric point with no size. Nothing in the observable universe behaves this way. Every object that has ever been measured has spatial extent. Every particle in the standard model that appears point-like in current experiments has only appeared point-like down to the resolution of the instruments used to probe it. Below that resolution, the structure is unknown, but not necessarily absent. The assumption that a point of zero size containing finite mass is physically meaningful is not an observation. It is an extrapolation of mathematical machinery into a regime where that machinery was never tested and where its foundations almost certainly do not hold. Those foundations are the assumptions of classical spacetime. That space is a smooth, continuous geometric structure that can be divided into arbitrarily small regions without limit, that a point is a meaningful location, that the geometry of spacetime at arbitrarily small scales resembles the geometry of spacetime at the scales where general relativity was developed and tested. Quantum mechanics has something very specific to say about those assumptions, not a vague objection or a philosophical reservation. A precise quantitative statement about what happens when you try to confine anything, matter, energy, information, to a region smaller than a certain scale. A statement that follows from the most fundamental principle of quantum mechanics, and that applies universally to everything the theory describes. That principle is the uncertainty principle, and what it does to the idea of a point, to the concept of zero volume containing finite mass, is not a correction or a modification. It is a structural prohibition, a statement that the situation general relativity predicts at the singularity is not just extreme. It is forbidden by the quantum mechanical description of reality at the deepest level that description currently reaches. To see exactly why, you need to see what the uncertainty principle actually is, not the popular version, which describes it as a limitation on measurement, the real version, which describes it as a fundamental feature of what it means for a physical quantity to have a value at all. There is a scale in physics that does not belong to any single theory. It was not derived from quantum mechanics alone, or from general relativity alone. It emerges when you take the fundamental constants of both theories and ask at what length, time, and energy they must both apply simultaneously and with equal weight. That scale is the Planck Scale. The Planck length is approximately 1.6 times 10 to the power of negative 35 meters. A proton is roughly 10 to the power of negative 15 meters across. The Planck length is 20 orders of magnitude smaller than a proton. It is to a proton what a proton is to the distance between the Earth and the Sun. No current instrument can probe it directly. It is a scale derived entirely from the constants of the two theories themselves. Those constants are three: the speed of light from special relativity, the gravitational constant from general relativity, the reduced Planck constant from quantum mechanics. Combine those three in the only dimensionally consistent way, and the Planck length falls out. No free parameters, no adjustable assumptions, just the constants pointing at a scale where both theories must apply at once. What happens at that scale is the central unsolved problem of theoretical physics. Below the Planck length, the quantum fluctuations of spacetime geometry become comparable to the geometry itself. Spacetime is no longer a smooth background on which quantum fields propagate. It is itself subject to quantum uncertainty. The concept of a definite distance between 2 points becomes undefined. The smooth, continuous structure that general relativity uses to describe spacetime ceases to be a valid approximation. Now consider where the singularity sits relative to this scale. The singularity is reached when curvature diverges to infinity, but curvature passes through the Planck Scale on the way to infinity. There is a moment in the approach to the singularity when the density reaches the Planck density and the scale of the region being described reaches the Planck length. At that moment, general relativity's own foundations cease to hold. The theory is not just producing wrong answers, it is being applied outside the domain where its assumptions are valid. The singularity may therefore not be a feature of the actual universe at all. It may be an artifact of extrapolating a theory beyond its breaking point. A map predicting the road continues straight, when the map itself only remains accurate to a certain distance, and the road bends sharply just past the edge of the page. What replaces general relativity at the Planck scale is unknown. No complete theory of quantum gravity exists, but the constraints are clear. It must reproduce general relativity at larger scales. It must reproduce quantum mechanics where quantum mechanics works, and it must produce finite answers where general relativity currently returns infinity. Before those candidate theories can be examined, the quantum mechanical objection to the singularity needs to be stated precisely. Because the uncertainty principle does not just suggest infinite compression is unlikely, it derives a minimum size for any confined system from first principles, and that minimum size is not zero. The uncertainty principle is usually introduced as a statement about measurement, that you cannot measure the position and momentum of a particle simultaneously with arbitrary precision, that there is an irreducible fuzziness no improvement in instruments can eliminate. That description understates what the principle actually is. The limitation is not on measurement, it is on the quantities themselves. Position and momentum are not two independent properties a particle possesses simultaneously, and that we merely struggle to pin down at the same time. They are linked by the structure of quantum mechanics in a way that makes their simultaneous precise definition impossible at the level of reality itself, not at the level of our knowledge, at the level of the thing. The precise statement is this: the uncertainty in position multiplied by the uncertainty in momentum must always exceed a fixed minimum value set by the reduced Planck constant. Make the position uncertainty smaller, and the momentum uncertainty must grow to compensate. The product cannot drop below that minimum, ever, for any particle, under any circumstances. Now apply this to compression. Confine a particle to a smaller region, and its position uncertainty shrinks. But as position uncertainty shrinks the momentum, uncertainty must grow. Larger momentum uncertainty means the particle has access to a wider range of momentum values. Some of those values are large. A particle with large momentum has large kinetic energy. Compress the region further, and the minimum kinetic energy the particle must possess grows with it. This is universal. Every particle confined to every region of space must possess a minimum kinetic energy determined by the size of that region. Smaller region means larger minimum energy. The relationship is exact and inescapable. What does this do to the singularity? The singularity requires finite mass compressed into zero volume. Zero spatial extent means zero position uncertainty. Zero position uncertainty requires infinite momentum uncertainty. Infinite momentum uncertainty means the particle must possess arbitrarily large kinetic energy. Arbitrarily large kinetic energy means arbitrarily large mass via the equivalence of mass and energy. More mass means stronger gravity. Stronger gravity means more compression, which demands more kinetic energy, which generates more mass. The situation is not just unstable, it is self-contradictory. The quantum mechanical requirements for confining matter to a point generate the very energy that prevents the confinement. The uncertainty principle does not say the singularity is hard to achieve. It says the singularity is a configuration quantum mechanics structurally forbids, not approximately, not under ordinary conditions, forbids as a direct consequence of what position and momentum fundamentally are. This is the precise nature of the conflict. General relativity says collapse must produce a point of infinite density. Quantum mechanics says a point of infinite density cannot exist because confining matter to a point generates unbounded energy that resists the confinement. Two frameworks, two answers, both derived from theories tested to extraordinary precision in every domain where they have been applied. Something must give. Either general relativity is wrong about the endpoint of collapse, or quantum mechanics is wrong about minimum confinement size, or both are approximations to a deeper theory that produces a different answer entirely. Every approach to quantum gravity is attempting to construct that deeper theory, and the place it must begin is the scale where both frameworks simultaneously demand to be taken seriously and where their demands cannot be reconciled. In 1974, Stephen Hawking did something that nobody expected. He applied quantum mechanics to the region just outside the event horizon of a black hole and found that the black hole was not black. It was glowing, not because anything inside was escaping. Nothing inside the event horizon can escape, but the event horizon itself, the boundary between the interior and the exterior, sits in a quantum mechanical vacuum, and the quantum mechanical vacuum is not empty. In quantum field theory, the vacuum is a seething background of fluctuations, pairs of particles and antiparticles continuously appearing and annihilating, borrowing energy from the vacuum and returning it almost instantly. Under normal conditions, these virtual pairs appear and disappear without consequence. But at the event horizon, the situation is different. A pair appears straddling the boundary. One particle on the outside, one on the inside. Before they can reunite and annihilate, the one on the inside crosses the horizon. The pair cannot recombine. The outside particle escapes as real radiation. The inside particle carries negative energy into the black hole, reducing its mass slightly. From a distant observer's perspective, the black hole is emitting radiation, slowly, at a temperature inversely proportional to its mass. A stellar mass, black hole radiates at a temperature so close to absolute zero it is unmeasurable against the cosmic microwave background. But the principle is exact. The black hole loses mass. Over an extraordinarily long timescale, it evaporates entirely. This result stitched quantum mechanics and general relativity together for the first time, and the seam immediately produced a problem that neither theory could resolve alone. Hawking radiation created a crisis that sits unresolved at the center of theoretical physics to this day. The crisis is about information, not information in the colloquial sense of facts and data, information in the precise quantum mechanical sense, the complete description of a quantum system, every property of every particle, every correlation, every entanglement, the total specification of what a system is at the quantum level. Quantum mechanics has a fundamental rule about information. It cannot be destroyed. Every quantum process is reversible in principle. Given the final state of a system, you can always reconstruct the initial state. The laws of quantum mechanics are time-symmetric at the fundamental level. Information is conserved absolutely. Now consider what happens when matter falls into a black hole. The matter carries quantum information, the precise quantum states of every particle composing it. Inside the event horizon, that information is causally disconnected from the rest of the universe. Nothing carrying it can escape. The black hole then slowly evaporates through Hawking radiation, but Hawking's calculation showed that the radiation is thermal, random, carrying no information about what fell in. A black hole formed from a collapsed star and a black hole formed from an equivalent mass of any other material would produce identical Hawking radiation. When the black hole evaporates completely, the information that fell in is gone, not hidden somewhere, not encoded in correlations too subtle to detect. Gone, destroyed, permanently erased from the universe. This directly violates quantum mechanics, a theory that has never been observed to fail in any experiment ever conducted, says information cannot be destroyed. A theory equally precise and equally tested says it can. The two theories are not just disagreeing about the singularity now, they are disagreeing about what happens at the event horizon, about the fundamental nature of quantum information in a gravitational field. This is the information paradox, and its attempted resolution produced something nobody anticipated, a conclusion so uncomfortable that it forced physicists to choose between two principles each considered inviolable. For decades, the information paradox was treated as a problem for the future, something a complete theory of quantum gravity would eventually resolve. The assumption most physicists held, largely following Hawking's own intuition, was that information somehow escaped encoded in subtle correlations in the Hawking radiation, invisible to any simple calculation but present nonetheless. The black hole would evaporate and the information would be out there in the radiation, scrambled beyond any practical recovery but conserved in principle. In 2012, 4 physicists, Ahmed Almhiri, Donald Marolf, Joseph Polchinski, and James Sully, showed that this comfortable assumption was internally inconsistent. Their argument is known as the Firewall Paradox, and it did not just challenge the proposed resolution, it showed that any resolution to the information paradox requires abandoning one of 3 principles that physicists had considered beyond question. The 3 principles are these. First, information is conserved. Quantum mechanics is correct and information escapes in the Hawking radiation. Second, an observer falling freely into a black hole experiences nothing unusual at the event horizon. This is the equivalence principle, a foundational assumption of general relativity. A freely falling observer should feel no local effect at the horizon. Third, quantum field theory works normally in the low curvature region near the event horizon of a large black hole. Almhiri and colleagues showed these 3 principles cannot all be true simultaneously. The argument is precise. For information to escape in the Hawking radiation, the late radiation must be entangled with the early radiation already emitted. But quantum mechanics forbids a particle from being simultaneously entangled with 2 different systems. The outgoing radiation cannot be entangled with both the early radiation and with its partner inside the horizon. One entanglement must be broken. Breaking the entanglement with the interior partner means the infalling observer does not encounter smooth, empty space at the horizon. They encounter a wall of high-energy radiation, a firewall. The equivalence principle is violated. The horizon is not locally unremarkable, it is lethal. The firewall paradox does not solve the information paradox. It sharpens it into an explicit choice. Accept that information is destroyed and abandon quantum mechanics. Accept the firewall and abandon general relativity's equivalence principle. Or accept that quantum field theory breaks down near the horizon in some way not yet understood. Every option requires surrendering something previously considered fundamental. Loop quantum gravity starts with a question general relativity never asks. What if spacetime itself is not continuous? General relativity treats spacetime as a smooth, differentiable manifold, a fabric that can be bent and curved but that is fundamentally continuous. divisible into arbitrarily small regions without limit. No minimum length, no discrete structure, just smoothness all the way down. Loop quantum gravity removes that assumption. It applies the quantization procedure of quantum mechanics directly to the geometry of spacetime. The result is a spacetime that is not smooth at the smallest scales. It is discrete, composed of finite indivisible units of area and volume, a minimum length of approximately the Planck length, a minimum area of approximately the Planck area. Spacetime below those scales does not exist, not because it is too small to measure, because there is no spacetime there to measure. The discrete structure of spacetime in loop quantum gravity is described by mathematical objects called spin networks. These are graphs whose edges carry quantum numbers representing areas and whose nodes carry quantum numbers representing volumes. The smooth spacetime of general relativity emerges from these networks at large scales, the way the smooth surface of water emerges from the discrete molecules composing it. What does this do to the singularity? In loop quantum gravity, the singularity cannot form. The compression of matter toward a point is halted when the density reaches the Planck density. At that point, the discrete structure of spacetime produces a repulsive quantum pressure, not the degeneracy pressure of fermions, but a geometric pressure arising from the impossibility of compressing spacetime below its minimum quantum of volume. The collapse does not terminate at a singularity, it bounces. The infalling matter reaches maximum compression at Planck density and then rebounds. In the context of black holes, this suggests the interior does not contain a singularity, but a region of Planck density matter that may eventually tunnel out or connect to a new expanding region of spacetime, a quantum bounce replacing the classical endpoint. The singularity is not resolved by new physics arriving from outside. It is resolved by the quantization of spacetime geometry itself, removing the possibility of the infinite compression general relativity predicts. String theory approaches the singularity from a completely different direction. Where loop quantum gravity quantizes spacetime geometry directly, string theory starts by replacing point particles with one-dimensional objects. Strings. Tiny loops or segments of energy, whose different vibrational modes produce the different particles of the standard model. The electron is a string vibrating one way. The photon is a string vibrating another way. Every fundamental particle is the same kind of object expressing different modes of vibration. This replacement has an immediate consequence for the singularity. Point particles can be compressed to a geometric point with zero size. Strings cannot. They have a minimum length set by the string scale, a length comparable to but not identical to the Planck length. You cannot compress a string to a point any more than you can compress a rubber band to a geometric point, while it remains a rubber band. The extended nature of the fundamental object introduces a minimum size that removes the possibility of infinite compression at the level of the theory's basic constituents. But string theory's most direct response to the black hole singularity comes from a proposal called Fuzzballs. In classical general relativity, a black hole is described by almost nothing: its mass, its electric charge, and its rotation rate. 3 numbers. Every black hole with the same 3 numbers is identical regardless of what it was made from. All information about the infalling matter is lost behind the horizon. Fuzzball theory proposes that this description is incomplete, that what general relativity describes as a smooth, empty interior with a singularity at the center is actually a dense quantum mechanical object, a ball of strings and brains, the higher dimensional objects string theory allows, packed together at the string scale, filling the entire volume inside what would classically be the event horizon. There is no interior in the general relativistic sense, no smooth space-time inside, no singularity. The entire object is a quantum mechanical structure with its information encoded in the configuration of the strings composing it. The Hawking radiation it emits carries that information out, resolving the information paradox by removing the featureless interior that caused it. The fuzzball is not a small correction to the black hole. It is a completely different object that reproduces the external gravitational field of a black hole while replacing its interior with quantum mechanical structure all the way down. Every candidate resolution to the singularity, the quantum bounce of loop quantum gravity, the fuzzball of string theory, the firewall, shares one deeply uncomfortable feature. None of them are currently testable. The singularity sits behind the event horizon. The event horizon is not just a practical barrier, it is a causal one. No signal of any kind can travel from inside the horizon to outside it. Whatever is happening at the singularity, whatever quantum gravitational physics is resolving or replacing it, is permanently shielded from any external observer. Not shielded by technology we lack, shielded by the causal structure of space-time itself. This places the singularity in a unique category among physical problems. Most unsolved problems in physics are unsolved because the relevant experiments are difficult or expensive, or require instruments not yet built. The singularity is unsolved in a deeper sense. Even a perfect instrument capable of probing the Planck Scale would return no information about the interior of a black hole if operated from outside the horizon. The only observer who could in principle gather information about the singularity is one who crosses the horizon, and that observer cannot send the information back. There are indirect routes. The Hawking radiation carries information about the black hole in principle, even if extracting that information is practically impossible. Gravitational wave observations of black hole mergers probe the geometry of space-time near the horizon and constrain the properties of the compact objects involved. The image of the black hole at the center of the galaxy M87, captured by the Event Horizon Telescope in 2019, showed the shadow of the event horizon in precise agreement with general relativity's predictions. But none of these observations reach the singularity. They probe the exterior geometry, the causal structure near the horizon, the properties of the object as seen from outside. The interior remains inaccessible. This is not a temporary situation awaiting better telescopes. It is a permanent feature of the problem. The singularity may be the only physical prediction in the history of science that is in principle unobservable from outside the system producing it, which raises a question that cuts deeper than any technical difficulty. If a prediction cannot be tested even in principle, does it describe something real, or does it describe only the limits of the theory making the prediction? A singularity is not a place, it is not an object, it is not a region of extreme but finite density that future instruments might someday probe. It is the point where the mathematical description of space-time reaches values the theory cannot assign physical meaning to, where the map runs out, where the road the equations have been following arrives at an edge and stops. That is the definition the descent has earned. General relativity predicts it as a theorem, not a feature of idealized solutions, but a mathematical inevitability under conditions the real universe satisfies. Quantum mechanics forbids it as a structural consequence of what position and momentum fundamentally are. The uncertainty principle does not allow the zero-volume infinite density configuration general relativity demands. The two theories have been aimed at the same point and returned irreconcilable answers. The singularity is therefore two things simultaneously: a prediction and a failure. A prediction because general relativity produces it honestly and inevitably from its own equations. A failure because the prediction itself signals that general relativity has been pushed beyond the boundary where its foundations hold. Infinite density is not a description of physical reality. It is a description of a theory that has exceeded its range. What lies beyond that range is the central open question of theoretical physics. Loop quantum gravity replaces the smooth spacetime that produces the singularity with a discrete geometry that cannot be compressed below a minimum scale. String theory replaces point particles with extended objects that carry a minimum size into the heart of the collapse. Both frameworks dissolve the singularity by removing the assumptions that produce it. Neither has been confirmed by observation. What the singularity actually is, at the level of a complete and confirmed theory of quantum gravity, remains unknown, not approximately known, not known up to a few technical details, genuinely unknown in a way that places it among the deepest unsolved problems in all of science. But unknown is not the same as meaningless. The singularity has been one of the most productive failures in the history of physics. The information paradox it generates has driven 50 years of theoretical work. The firewall argument it produced forced a confrontation between quantum mechanics and general relativity sharper than any previous one. The candidate theories attempting to resolve it have produced new mathematics, new ways of thinking about space-time, and new questions about the nature of information that reach far beyond black holes. The singularity is where two of the greatest intellectual achievements in human history meet and find themselves insufficient. Where the universe is telling physicists that the current description of reality is incomplete, and where the next description, whatever it turns out to be, must begin.